talks will be on Zoom as well. Hi, good morning. Myself Vinayak, embedded NVM product manager at Global Foundries. As the chair of IEEE Magnetics this year, I welcome you all for this 13th Symposium on Magnetics. I never forget, the first time I attended IEEE Symposium, I think almost 15 years ago as a PhD student. It was very interesting to participate as well as present and also learn from other experts. Here we are today on 13th Symposium. I'm pretty sure all of you will have a great time. We have around 9 keynote talks, 2 public lectures, and 2 plenary talks. Thanks to all distinguished guests for coming here, as well as traveling from abroad to Singapore. Warm welcome to you all. I wish you have a great 2 days event and take full advantage of this program to have a networking session with the other experts. Coming from industry, I can only say that today there are a lot of emerging technologies being tried out in industry, and magnetics technology is one of the forefront technology solutions today. Because I myself have witnessed, I worked on spintronics as a PhD student, all the way to driving non-volatile memory by magnetic-based memory into the microcontroller units. And this is only growing because, as you might know, with the growing interest in AI, ML, as well as autonomous vehicles, we are talking about 10 times higher semiconductor chips coming into automotive. And all customers are looking for high-speed, robust, and as well as low-power technologies. And some of the magnetics concept, whether it could be memory, a sensor, or it could be even some of the back popping phenomena. It's a kind of reversible and free layer as to generate spike. These are all can definitely serve many products in semiconductor industry. But I think from a research point of view, identifying the right problems which industry facing and providing that right solution is the key. I'm pretty sure all of us take that advantage to take this magnetic research to get the full potential of it. With that, thanks to all of you. Finally, I would like to thank organizing committee led by Dr. Ramu, Dr. Durgesh, and Professor Prem, and also the IEEE Magnetics Chapter Committee for support. Thank you.
Good morning, everyone. My name is Durgesh. So with the welcome speech, we start the first session of 13th Magnetics proposals chapter. So this session has 2 talks. The first talk is given by from NTU Singapore. The title of the talk is Atomic Scale Fermions in Bomb. Let's welcome.
Good morning, everyone. I would like to start by thanking the organizers for organizing this event and giving me a chance to share some of my results with you all. This is my first time attending an IEEE Magnetics Symposium, and I look forward to learning from you a lot. Okay, for my talk, I chose a topic which I think will be most relevant to most of you given your research interests. Although I have to admit this is not a completed work, it's still ongoing. So whatever results I will present are not yet published. So, but I think you will find it interesting. In particular, I will talk about atomics. What happened? It was working. Slideshow. Oh, quit. Duplicate. Oh, duplicate. Oh, I don't know. Sorry for the interruption. Okay.
Go to slideshow, then duplicate.
Slideshow and then duplicate.
Yes. So below this, we'll just drag this out. Yeah,
But then zoom. Let's zoom it
below this, this
below which. Oh,
maybe just drag the
oh, drag the zoom one.
then yeah, select it.
I'll use slideshow.
Okay, yeah, this is fine.
This is fine.
Now we
Oh, what? Oh.
sometime.
No, but where is the pointer?
Yeah, it's coming.
Oh, wait.
This cursor.
Hmm?
This cursor.
Oh. Wait. If I choose this one. Okay. Okay, thank you. Frame and sorry for the interruption. Okay, let's continue. My collaborators in this work are Nyabant and Munir. In other words, they are the ones who did most of the work. Here is a brief outline of my talk. I will start with a, actually just, I don't. There's something. Yeah, but what is, okay, let's just disconnect this one. And then let's see if it works now. Why is it not? Oh. Okay, whatever works, we will use this. Hmm?
This
Yeah.
pointer, then it will work.
Oh, okay. Thank you, Durgesh. So here is an outline of my talk. I will start with a brief discussion on magnetic skyrmions. Why do we study them? How do we detect them? And what are some of the interesting properties? Then I will move on to the stabilizing mechanism for most commonly studied skyrmions, which are driven by Zaloshinsky-Moria interaction. After that, I will move on to the new class of skyrmions that have been very actively being pursued in the last few years, which are atomic scale skyrmions. I will talk about what are the origin, what are the stabilizing mechanism that are, what is the origin for such skyrmions, and I will tell you that these impart some special properties that is not observed in the DMI-driven skyrmions. I will pick one particular compound, gadolinium, ruthenium, aluminium, and discuss its crystal structure and properties, experimentally measured properties, following which I will talk about modeling and simulation results, and then I will conclude with a brief summary. So skyrmions are complex spin textures which arise out of competing interactions. It consists of a single spin pointing up at the center, following which the spins around it um, uh, deviate away from the vertical direction, coming to a full pointing down. So it forms a vortex-like structure, and that is schematically shown here. And so depending on whether you have only radial outward flow, or you have on top of that you have an axial rotation also, you get what are known as nail skyrmions or block skyrmions. These, importantly, these act as magnetic quasiparticles and are topologically non-trivial, that is, they carry topological charge, and they act as quantized emergent magnetic field. These are the two properties that give rise to most of the interesting physical phenomena associated with skyrmions. The study of skyrmions is interesting from both fundamental and practical points of view. From a fundamental standpoint, we get an insight into quantum many-body physics, and in particular, the emergence of complex magnetic textures out of competing interactions. People have moved to a large number of non-coplanar structures like biskyrmions, Hopfians, and many others. So the other interesting thing is that since there are lots of practical or experimental systems where you can controllably tune the emergence and propagation of skyrmions, it gives you a huge playing field to study skyrmions in a controllable manner, or non-coplanar structures, spin structures in a controllable manner. From a practical point of view, Vinayak said that we are, as an industry, we are moving towards more and more new technologies, and one of the potential uses is to be, or skyrmions is to be used as for storage and processing of information in logic and memory devices. Here, the topological character gives its protection against against noise and disorder and other defects. And these are promising candidates for future racetrack type memory logic computing technologies. So these are some practical applications that has been pursued and are being pursued. Now, these are complex spin textures. How do you detect them? The conventional go-to method in quantum magnetism is neutron scattering, but neutron scattering gives you long-range magnetic ordering. Here we are talking about short range at nanometer level resolution of real in real space. So fortunately, because of the non-coplanar spin configuration, they interact with optical and X-ray photons as well as electrons, which can be used to develop methods to detect real space spin configurations at a nanometer resolution. In particular, there has been many recent advances in these technologies, and there are 4 primary probes to detect real space configuration of skyrmions. This includes Lorentz TEM, although they are limited to electron transparent thin film specimens. Spin polarized STM, is another very powerful method that can detect ultra small skyrmions. Then we have magnetic force microscopy and also MOC microscopy based on magneto-optical curve effect, which are primarily used for large-scale skyrmions. Now, skyrmions have many interesting properties. Here I will discuss only a couple of them, which are going to be relevant in the coming discussion. First is the topological Hall effect. What is the topological Hall effect? Topological Hall effect is when you send electrons through a sample and you observe a Hall effect without applying any external magnetic field. So here, the skyrmions, because of their non-coplanar spin configurations, they act as quantized source of magnetic charge. So when itinerant electrons travel through these a lattice of skyrmions, that is a periodic array of static skyrmions, they pick up Berry phase because of strong coupling to the local magnetic moments. So that Berry phase acts as an effective or statistical magnetic field, which imparts a Lorentz force, which in turn results in a transverse current, which is known as the topological Hall effect. So you are not applying any extra magnetic field. You are the transverse force is generated because of the Berry phase that the electrons pick up while they travel through skyrmions. It picks up a Berry phase because of the non-coplanar configurations of spin configurations that to which the electrons couple strongly. Here, the smaller the skyrmions, the stronger the local EMF. This will become important when I talk about atomic scale skyrmions. The other equally interesting phenomenon is skyrmion Hall effect, where the skyrmions are not localized and static, but are mobile. Here, the skyrmions carry zero electric charge, so they should not be affected by any Lorentz force. But when you send spin polarized current through skyrmions, there is a spin transfer torque generated by the spin Hall effect. And this spin transfer torque drives the skyrmions. It drives it both longitudinally, but also, importantly, there is a transverse force on the skyrmions. In most cases, this is a bad thing, because you cannot drive a skyrmion in a straight line through a sample. But on the other hand, this is a interesting phenomena, and we have to take advantage of that, or rather, instead of looking at the negative aspects, find proper applications of it. Okay, I told you that skyrmions are stabilized by interplay between competing interactions. For most of the skyrmions that I just discussed, and in fact, almost all of the skyrmions prior to maybe 2019, these are now referred to as DMI-driven skyrmions. Here, there are the two most important interactions that lead to the formation of skyrmions are Heisenberg exchange interaction and Dzieloszynski-Moria interactions. Heisenberg exchange can be either ferromagnetic or antiferromagnetic. Most importantly, Heisenberg exchange favor collinear arrangement of the spins, either parallel or antiparallel. On the other hand, Dzieloszynski-Moria interaction is an antisymmetric interaction, which can be either intrinsic or it can be induced at the interface by forming a heterostructure with heavy metals. It favors, most importantly, it favors perpendicular alignment of the spins. So this is what TM interaction looks like. So this term is maximized when SI cross SJ is maximum, which is when they are perpendicular. So Heisenberg interaction favors parallel alignment, whereas collinear alignment, whereas DM interaction favors perpendicular alignment. It's a competition between these two tendencies that result in the formation of skyrmions in this system. In addition to that, there are additional interactions which include long-range dipolar interactions, exchange anisotropy, single ion anisotropy that are almost always there in real materials. While they change the detailed nature of the skyrmions, these are not essential ingredients in the formation of skyrmions. Okay, that's all I'm going to talk about the DMI-driven skyrmion. Okay, no, let's go through a few examples. So for this conventional DMI-driven skyrmions, they are primarily observed in non-centrosymmetric systems with systems with broken inversion symmetry. This can be either bulk compounds like MNSI or artificial heterostructures where you form a heterostructure of a thin film of a magnet and a heavy metal. Heavy metals have strong spin orbit coupling, which induce an effective DMI at the interface of the magnetic material, which in turn nucleates the skyrmions. In fact, that has been at NTU. That has been quite an active area of research. So, but all these require non-centrosymmetric bulk materials or inversion symmetric broken heterostructures. On the other hand, recently, in the search for ever smaller skyrmions, people have discovered atomic scale skyrmions. Now, DMI-based skyrmions, the size ranges between somewhere in the hundreds of nanometers. It can go down below 100 nanometer, but not by much. On the other hand, people have been searching for smaller scale skyrmions in the range of 1 to 10 nanometers. One to 10 nanometers. And what people have found is that the route to such small scale skyrmions lies not in cranking up Yaloshinsky-Moria interaction, but rather create a completely new paradigm. That is, instead of looking for DMI-driven skyrmions, we are now looking at geometrically frustrated lattices with longer range Heisenberg type interactions and absolutely no DMI. So the combination of geometric frustration and interaction frustration driven by long range Heisenberg interactions, that results in miniaturization of skyrmions. So these systems, these are centrosymmetric systems with no broken inversion symmetry. Instead, what is prominent here is frustration, both geometric frustration coming from the lattice structure, as well as frustrated interactions coming from longer range interactions. These results in not just this miniaturization of skyrmions, but also comes imparts a host of new properties. These include near degeneracy of left and right-handed screws, which are precursors to the skyrmions, and near degeneracy of nail and block type skyrmions, which also leads to time-dependent helicity changes. That is, by applying a small amount, a small external field, you can change the helicity of the skyrmions. There arises mixed phases and near degeneracy of skyrmions and anti-skyrmions. This is very different from what is observed in DMI-driven skyrmions, where you fix a preferred axis by this DM vector. So having said that, there has been a few compounds that have been reported as or have been discovered, where people have reported the existence of atomic scale fermions. These include gadolinium-based gadolinium, palladium, silicon on triangular lattices, but I will talk about gadolinium, ruthenium, aluminium on a breeding cargo lattice. So this is a chiral metallic magnet, meaning that it is a metallic magnet where there are localized moments carried by the gadolinium 3+ ions. So these are huge moments. So these behave as classical spins. Aside from these localized moments, there are also itinerant electrons that give rise to metallicity in this material. Structurally, this compound crystallizes in the hexagonal p63mmc space group. It consists of buckled ruthenium aluminum layers and planar gadolinium aluminum sheets stacked along the C-axis. So the magnetic moment carrying gadolinium ions form a breeding cargo lattice. Breeding cargo lattice, just for the sake of completion, let me just explain what it is. It's in the cargo lattice, you have these constituent triangles which are normally identical in the regular cargo lattice. Breeding cargo lattice, these are these upward facing triangles, and the downward facing triangles have different sides, lengths of the different sides. So this is called the breeding cargo lattice. Here, in case of this compound, the distance between nearest neighbor gadolinium ions, these ions, the ratio of this distance, nearest neighbor gadolinium ions in the smaller triangles to the nearest neighbor distance between gadolinium ions in the larger triangles is approximately 0.73. Huh? Coming. Aha, here. So now at zero magnetic field, applied field, this is what the behavior looks like. The magnetic susceptibility exhibits Curie-wise behavior at higher temperatures. The Curie-wise temperature deducted from the high temperature behavior is about 70 Kelvin, which points towards a dominant ferromagnetic exchange. But you do not observe any long-range magnetic order all the way down to 18.6 Kelvin, which indicates that there must be some competing interactions which is preventing the onset of magnetic order at higher temperatures. Indeed, in the specific heat measurements, you observe two sharp anomalies at 17.2 Kelvin and 18.6 Kelvin. And based on real space spin imaging with resonant X-ray scattering, small angle neutron scattering, and Lorentz TEM, people have found that in the range, first there is when you cool down the temperature, first there is an onset of sinusoidal spin order in the hexagonal AB plane. So you form some spin or magnetic ordering in the plane, and at a slightly lower temperature, you there is an onset of 3D helical order. Interestingly, the helical pitch length is 2.8 nanometers. This is what determines when the size of the fermions when they are stabilized. This compare that to manganese silicide, where the pitch length is 19 nanometers. So there is almost a factor of what 6 to 7 between the pitch lengths, and that is you already see that it favors small skyrmions. And this is the full field-induced phase diagram as you vary the applied magnetic field and the temperature. You go through a host of very interesting phases at low values of the field over a wide range of temperatures. You form helical order. That is what we said at below 17.2 Kelvin, you form a helical order. As you keep increasing the magnetic field at low temperatures, you enter what is known as called as a transverse conical phase, where you induce this non-coplanarity, but you still don't have fully formed skyrmions. At slightly higher temperatures, over a finite range of temperatures and field, you stabilize a skyrmion lattice, which is shown here. And right away, you will see that the size of the skyrmions is much smaller than, is only a few lattice sites wide. And then there is a unique fan phase at higher magnetic fields, which we will not get into. Our primary focus is on this small scale skyrmions. So that is determined from magnetic measurements. And what about transport measurements? The main interest in this compound arose because of the large thermal Hall effect that it exhibits. It shows, there is non-zero integer winding number of the magnetic texture because of the skyrmions. This form give rise to Berry phase of conduction electrons, and that results in thermal Hall effect, which is measured to be large in this material and is a direct evidence for chiral nature of the skyrmion lattice phase. So with that experimental background, we now move on to microscopic modeling. Our goal is to develop a minimal microscopic model to understand the emergence of these atomic scale skyrmions and any associated behavior. So we start with this Hamiltonian, which looks pretty ugly, but this is what we have. We have nearest neighbor ferromagnetic exchange denoted by J1 and J1 prime. J1 and J1 prime denote the nearest neighbor exchange on the smaller and larger triangles respectively. You have a next nearest neighbor, J2, exchange interaction, which is antiferromagnetic in nature. This is what brings in the interaction-driven frustration. So first of all, the Kagome lattice is geometrically frustrated. On top of that, you have these longer range interactions, which also leads to interaction frustration. On top of that, just to be general, we also included exchange anisotropy denoted by alpha, as well as single ion anisotropy denoted by A. So that is the Hamiltonian describing the localized magnetic moments and their interaction. Now, remember, I told you that this is a metal. So you have itinerant electrons on top of these localized moments, which are described by simple tight binding model. That is, there is nearest neighbor hopping on these triangles, and we take T and T prime in the same ratio as J1 and J1 prime, which we take to be about 0.75 following the experimental measurements. So the idea is that the hopping strength depends on the bond distance. And finally, there is this coupling, classical Kondo coupling, describing the interaction between the localized moments and the itinerant electrons. So we used a classical Monte Carlo simulation to identify, for here, we are just focusing on the low temperature phases. What we find is that at zero field, you have a helical phase, which is identified by two peaks in the static structure spin structure factor to symmetry related peaks. And as you increase the magnetic field, there is a transition to a skyrmion lattice, which is identified by its characteristic 6-peak structure in the static spin structure factor. It consists of 3 non-equivalent Q vectors. So you can think of a skyrmion as a superposition of 3 helices with non-equivalent Q vectors. And this is exactly what we find for the intermediate phase. And finally, at higher fields, there is the spins are field polarized. It's interesting to note that the size of the skyrmions is only 2 unit cell big. So this is a breeding Kagome lattice. In a Kagome lattice, each unit cell consists of 3 sites. This is a breeding Kagome lattice, which means there are these 2 inequivalent triangles. So there is the unit cell consists of 6 sites, and here the skyrmion size is only 2 unit cell big. Now then we calculated the spin chirality, which is shown schematically here. The spin chirality is finite in the skyrmion phase, but also finite in the helical phase because of this anisotropy that we have included. So now we calculated the topological Hall effect or electron transport, calculated both the longitudinal and transverse electron transport in the presence of this in the skyrmion phase. And what we find is that the electron bands are renormalized due to coupling to the localized moments. They pick up a finite Chern number. And as such, when you calculate the conductivity, there is a clear signature of topological Hall effect, which you can understand as follows, that when this band is filled, that is, you raise the Fermi level to about this point, then you have a filled band which with a band with a finite Chern number, which results in a finite transverse conductivity. And then you fill up the other band, which has opposite Chern number, and the net transverse conductivity vanishes. And then similarly, when you go, in fact, this is plus 2, minus 2, plus 2, minus 1, plus 1, minus 2. So as you keep filling up the bands, you find that the topological Hall effect is reflected. Now, here is where I want to address the question, why do you find large topological Hall effect for smaller skyrmions as opposed to larger skyrmions? After all, this is a topological property, maybe 1 or 2 minutes. Topological property, so it should not depend on how big or small the skyrmions are, because as long as it's carrying a topological charge, then all it depends on is the fact that it carries a topological charge. But that's because we are not considering scattering mechanism here. Smaller skyrmions result in a electron mean free path. Smaller skyrmions mean that the electron mean free path in a clean sample is of the order of or greater than the skyrmion size. This results prevents loss of coherence due to scattering, and that results in large topological Hall effect. So the smaller the skyrmions, the larger the relatively the larger the relative electron mean free path, which results in smaller, fewer or less scattering loss, and that results in a large topological Hall effect. And that's the summary. Summarize frustration, both geometric as well as interaction, facilitates the formation of atomic scale skyrmions. This enhances the potential applicability of skyrmions in and opens up new areas of application. Additional physical properties further increases potential for practical application. Something I did not touch upon is this is a promising route to realizing quantum skyrmions. As the size of the skyrmions gets smaller, quantization effects become more pronounced, and we can realize quantum skyrmions in a real material. These have potential applications as qubits in quantum computers, and the discovery of new materials and advancement in characterization techniques mean that this is a field that is going to grow very fast in the near future. Thank you for your attention.
Myself. So because of the time limitation, we have time for one question.
Okay.
So I understand the interaction frustration. But what is it then?
Oh, geometrical frustration just means that if you have a triangle, marker, I don't, well, oh, you have a marker? Oh. Geometric frustration is just the standard that if you have a triangle on which you have antiferromagnetically interacting spins, so this they like to be paired in antiparallelly. Then if this is up, this is down, satisfying this bond, then where does this point to? If it points up, then this is not satisfied. This is satisfied. If it points down, it's the other way around. Yeah, it's spin glass. So what happens is that you have a large degeneracy of low energy states, and that is geometric frustration.
Then what is interaction?
Interaction frustration just means that even for, let's say for a square lattice that does not have geometric frustration, if you have nearest neighbor interaction being ferromagnetic and next nearest neighbor being antiferromagnetic, just as we considered here. So if you have nearest neighbor being ferromagnetic, then this will be your configuration that satisfies all the bonds, right? But now if you have a next nearest neighbor antiferromagnetic interaction, that competes with this ordering. So that is interaction frustration. Okay, and indeed for these long range interactions are driven by this RKKY type coupling, which oscillates with distance.
Thank you. Thank you, Mr. Pinaki.
Thank you. Thank you for your attention.
Should I make it like audio
This is
share? Okay. But it's not showing audio in Zoom, right? How do I share it and yeah. Directly? Okay. Is it working?
And
Can I check? Which one? Sorry, which? No, but this is fine. Oh, it's not working. Something. Okay. But it's not working. No. Sang. Oh no, the slide.
Yeah.
It's not working.
no, it's
It's not working, right? Okay.
because the software needs to be installed.
Oh, but just now it was working. Okay.
Even this one was not working.
Okay.
I think that's because
Installing. Is it?
no, even this one's also not working.
So
It's
me,
supposed to work, right?
but the computer is saying.
Right?
I think it's installing the software.
No, it's not installing. It's not that one.
Oh, sorry. Oh, yeah, the computer is saying. Sorry.
What?
Oh, both. Okay. Okay. Yes.
This one needs to be.
So which is up? Oh.
This is for this is for
Mm.
this is for screen sharing is possible.
Scaring is pause.
Stop again. Share again.
This one?
Yeah.
Is it okay? Okay. Okay.
All right. So the second talk of the session is by the James from A Star. The title of the talk is Studying Constant-Based Heterostructures for Efficient Spin-orbit parts. So let's welcome them.
Thank you all for coming. First of all, I would like to thank the Prof Prem and the IEEE Magnetic Society for this invitation. So today I will be talking about tungsten-based heterostructures for spin orbit torque. I'll get into details of why we're doing on tungsten and some fundamentals of spin orbit torque. So I'm a staff at Institute of Materials Research and Engineering, and was also a former PhD student here. Okay, so the talk is divided into 4 parts. Basically a preview of the spin orbit torque. Then I will for this talk, I will get into 2 examples of the directions that we are taking at ASAR based on tungsten test system, and conclude with some outlook. So first of all, I would like to acknowledge my colleagues that have worked on this project, and I'm going to present an overall work that we are currently doing here. Hongjing and Abhijit did the harmonic Hall measurement, Leeson did the SFMR, and our colleagues from ISPC helped with DFT calculation and micromechanics simulations. Also, our collaborators at NTU and University of Perugia. So initially, when we started this work about 4 years ago, the goal of the project was to get into ultra-fast write energy for memory technologies. Basically, we want the energy of writing information to be as low as possible and the write time to be as fast as possible. So basically, in this plot, we want to get into the bottom left corner of this plot. So there are several computing technologies, and with the development of STT RAM being superior over other technologies, it became possible for emerging techniques such as spin orbit torque and voltage control RAM to further improve on the work of STT. So these are quite interesting for applications in the cache memory and memory intensive computing. So with this motivation, we started entering the spin orbit torque space a few years ago. So a brief background. So the spin orbit torque MRAM, or the memory technology, the basic element is a magnetic tunnel junction. So unlike a traditional two-terminal magnetic tunnel junction, this one has a three-terminal where the read and write parts are separated. So one would send the electrical current in the right part, which is typically a heavy metal, and by the property of the spin orbit interaction in the heavy metal, there is charge there is spin imbalance in the heavy metal, which would lead to a torque on the ferromagnet sitting just above it. And this is how one could switch the magnetization of the ferromagnet. The read is basically tunneling magnetoresistance in this case. So the materials parameter one would try to optimize in this kind of structure is the spin Hall angle, which is just the ratio of the spin current to the charge current. And another important parameter here is that the spin polarization, the spin current flow and the charge current flow are all orthogonal to each other. So this would lead to some requirements, some critical requirements, especially in trying to switch a perpendicular magnet. So it's easier to switch a in-plane magnet as compared to a perpendicular. I'll get into details in the following slides. So there has been many development in this area with regards to development of a high or a good spin Hall angle system. While there's many interesting materials with regards to development of these materials on a 200 or 300 millimeter wafer platform, we are kind of restricted to basically three materials, which is tungsten, tantalum, and platinum. So out of these, tungsten, beta phase tungsten has the highest spin Hall angle. But what one would do is also try to optimize the resistivity in the channel, because a higher resistance would require a higher voltage that might not be suitable for the CMOS requirements. So in terms of materials development, more work was done on trying to build on this three materials platform, especially by looking at alloying or multi-layers. And there were some interesting developments with alloying. So this is where we started interested in trying to alloy or dope on these three materials platform. So while as I mentioned, in the 200 or 300 millimeter platform, we are restricted to three materials. But out of this, tungsten is the more suitable choice for here, because it can support both in-plane and out-plane magnetic tunnel junction. And for example, platinum cannot support out of plane magnetic tunnel junction, and it has a pretty large TMR, which means the read signal is high. However, the tungsten film typically likes to be in the alpha phase, which is a low spin Hall angle. So the challenge here is the channel thickness on these kind of deposition tools are limited to 4 nanometers. So we want to widen this this thickness transition window. And the other issue, of course, is the high channel resistance. So besides the spin Hall angle, one material parameter, the other material parameter that we started to look into is the Renshaw-Moria interaction. As I mentioned here, that there is an issue of switching a perpendicular magnet, because one would require a symmetry breaking. So there are many proposals to get to symmetry breaking in perpendicular magnetic tunnel junctions. And one of the ideas that we had was using Renshaw-Moria interaction, which is the exchange interaction, and it favors a spin spiral state. So in a nano size magnetic tunnel junction, the presence of DMI would tilt demagnetization at the edges. That would inherently break the symmetry and can lead to switching of magnetization, as shown in our work some years ago, where you have a plot of magnetization in the Z direction, and the x-axis is basically a electrical current, a pulse electrical current that has been passed through. So when D is equal to 0, the MZ basically goes to 0, and then once you remove the pulse, it could either be 0 or 1. But when you have a DMI, for example, the red line, then once you remove the pulse, it switches to one direction. So with that overview, I'll go to the first part, which is using tungsten tantalum based SOT channel. So what we did in this, so typically in a magnetic tunnel junction, it has the free layer and the reference layer part. The free layer typically has 3 components. One is it could be tantalum or tungsten as the channel, or it could also act as a boron getter. Then you have the cobalt iron boron, and then MgO. So this is the what we call as the half stack. So the half stack. So we typically develop the half stack first before developing the full magnetic tunnel junction. So in this case, I've shown an example of comparison of just tungsten and as well as the tungsten tantalum multilayer. So here in silicon alloy, we use submonolayer deposition to get this tungsten tantalum multilayer. And in either case, as shown for comparison, we can get permanent. We can get PMA, and once we develop the free layer, then we can go on building a full stack with these systems. So tungsten, as I mentioned, typically at low thicknesses, it is an alpha phase. As we increase the thickness, typically low thicknesses, it is in beta phase. As we increase the thickness, it transitions to alpha phase. In this particular example, where you have a tungsten tantalum multilayer, it is in the alpha phase. To recollect, the beta phase is a higher spin Hall angle. And this can be observed in both XRD as well as the resistivity measurement. So low resistivity is for alpha phase, and high resistivity is for beta phase. So just a side note that when I mean by the restriction of 4 nanometer thickness is after annealing, actually. So if one anneals these samples, then the beta phase is lost above 4 nanometers, roughly around 4 to 5 nanometers. Then we look at this text for DMI, so which is done by brilliant light scattering measurement. These were done by Dr. Sylvia from University of Perugia. So basically here, the stocks and anti-stocks correspond to creation and annihilation of magnons, and the difference in the counter propagating waves given by delta F is proportional to D. So one could do this experiment and to get the difference of delta F and determine DMI in the system. So as expected, because of the linear relations as in the previous slide, we do get a linear relation of delta F versus momentum. And from this slope, we can get the DMI in the system. So the DMI in the beta phase was found to be slightly lower than the alpha phase. And also the DMI, because here it's an interfacial property, right? So as you thin down the CFP, the DMI will increase, since it's coming from the interface between tungsten and CFB. Once we alloy, we could tune the DMI from to about 70% by different combination of tungsten and tantalum. The other thing here is that, as mentioned in the literature, we also got positive DMI or right-handed chirality for all the samples that we measured. The second parameter that we wanted to optimize is the spin Hall angle. So for this, we fabricate Hall bar stacks, Hall bar devices, and do the first and second harmonic measurements. And from the first and second harmonic signals, we can get the anti-damping light top, which is the BAD here. And we can use this BAD term to determine the spin Hall angle in system. So what we found is, well, our original quest was to get the value higher than beta phase tungsten, which is about -0.3. We find that while doping or making tantalum multilayers modulates the spin Hall angle, but it does not make it better than what has been reported so far. So, so with this, we looked into a different system, which is oxygen doping system in tungsten, to see if we can if we can make it better than the tantalum tungsten multilayer, because the spin Hall angle was not as high as we wanted. So here, what we did was we had a layer of tungsten deposition. Then we introduced oxygen plasma, and we repeat this over several layers. And what we found is that when we do this process and comparison with pristine tungsten, we could find that the tungsten is now in the beta phase for roughly about 9 nanometers. So this is a major improvement in terms of the critical thickness required to get the beta phase, and we were able to get a higher beta phase at higher thickness, either by changing the thickness of one repeat or changing the number of repeats. So in both experimental window, it was increased to the critical thickness required was increased to roughly 9 nanometers. If we look at the XPS of this system, so the left plot is the XPS data of tungsten spectra, and the right is for oxygen spectra. So the two big peaks at around 34 and around 32 are mostly coming from the metal tungsten peak, but there is so the top and the bottom plots are for our tungsten multilayer, and the one at the bottom is a tungsten oxide compound. So the main difference is around at 36, about roughly 36 EV, which corresponds to the tungsten oxide signal. We see that it's mostly a background in our multilayer. That means the amount of oxygen concentration in the system is very, very small. But of course, we know that there is oxygen in the system because we can see the oxygen spectra as well. That is in the right plot. So our collaborators at the ISPC looked at into some DFT calculations and basically look at the formation energy. So what we found is that if we put a little bit of oxygen, it helps. So the black and the red plots is for beta and alpha phase. So the higher the formation energy, or the lower the formation energy, the more stable it is. So if one puts even a little bit of oxygen, it favors the formation of beta phase. However, previous work showed that also from theoretical calculations that one wouldn't want to put too much oxygen in the system. So, and this is spin Hall conductivity determined for various tungsten system. So here, what they so this bar here is for pure beta phase tungsten in the theoretical calculations, and if one keeps on increasing the oxygen, for example, at 11%, it drops significantly. So and as one increases the oxygen doping further, so the spin Hall conductivity drops as well. So one would just put in a little bit of oxygen to stabilize the beta, but not reduce the spin Hall conductivity too much. So then, in terms of the half stack, we did several anisotropy measurements. So we measured the K effective as a function of the number of repeats as well as the CFB, and this showed the standard K effective thickness with CFB thickness, which means it drops down as we increase the thickness of the CFB because it's coming from the interface. However, for oxygen termination, we find that a measure of the plot here is actually an in-plane sample, and it only becomes PMA at higher CFB thickness or at high number of repeats. So the oxygen termination is not so interesting for us. And we have another issue with oxygen termination, which is the dead layer in the system is higher than what we want. So in terms of DMI measurement, this work is currently ongoing. I've shown that in the previous example, whether we use tungsten or tungsten tantalum or other formats based on tungsten system, we always got positive. But in this tungsten multilayer system, we got a negative DMI. This was measured by Suraj at NUS. We're still trying to figure out why the DMI in this system, the sign of the DMI has changed. And the value is also different in the case of oxygen termination, found it to be higher than tungsten termination. Then we come to the spin Hall measurement of this tungsten oxygen doped tungsten system. So as I mentioned that in the low thicknesses, the tungsten is in the beta phase and the high thickness is in alpha phase, right? So this is easily observed from the spin Hall measurement. So the red dots here is just pristine tungsten. And we can find that the value drops suddenly after it transition to alpha phase. And when we use the multilayer, we find that the value is high, even up to 9 nanometers. And the other thing is in our like 200 millimeter deposition platforms, we're not able to reach 0.3 that is quoted in literature. Well, these are all, of course, after annealing at 300 degrees Celsius. So, however, there is a caveat there because in the calculations, we assume that there is no planar Hall, but in fact, this value of eta, which is the ratio of anomalous to planar Hall effect, is pretty high because this is important because if eta is, let's say, about 0.5, then the value becomes, if you use the real value of eta, then it becomes unreasonable. So the assumption here is eta equals 0. So we have to consider that there is a caveat in this value of spin Hall angle. So then we look into another technique if we can get the value of spin Hall angle. So this one is called the ST-farm measurement. So here we send an RF current into the device here. This dot is the device. This is a GSG probe, and the RF current sends the magnetization to a resistance. Sorry. Okay. Yeah. Okay. So I'll just quickly go through the result. So what happens is that when so this is a typical ferromantic resonance that we have from this measurement, and by changing the DC current here, we can get the value of we can get a relation between the delta, which is the line width, versus the current. So this relationship will give you the value of Js, which is the spin current, and from here we can get the spin Hall angle. So from here, what we found is that if we look at the tungsten oxygen doped tungsten system, we find that the value is roughly close to slightly lower, but roughly close to what we have from the harmonic measurements. So we also tried with tungsten 4 nanometers, and without annealing the system, we find that it is slightly larger than the tungsten oxygen multilayers. And once we anneal this, the value drops significantly to about 40%, to a value of about 0.2, which is consistent with what we observe in the harmonic Hall measurements. So of course, in the harmonic Hall measurement, we can't do the as deposited condition because we need the system to be PMA. Okay, so I think I will quickly go through the MTJ part. This is how we do the MTJ fabrication in our ASR facility. We have a 3-inch cassette line, and then we develop the MTJ by using this 3-inch fabrication line. And this is a typical example of an MTJ. For an in-plane, we have an ellipse, and we can send current through this and switch the magnetization from top to bottom. Yeah, okay, so I'll come to the final point. So the goal of this project, basically, we want to build this technology by using, starting from the platform of materials, then we go on to devices and circuits and algorithms. So with this, we started with tungsten as a materials development and found that we could sustain this beta phase high spin Hall angle system up to 9 nanometers. Then we developed MTJ with very, very large CMI and decent current densities. And finally, the goal is to get into circuit integration, which requires a 2-terminal and 1 MTJ. And this is a SEM image of what we have with platinum. So you have the wires below connecting to the transistors and the MTJ on top. Okay, so I'll wrap up my talk with that. Thank you.
Talk is no good. What was it?
So for which sample? There are two samples.
Compare. Because I was working PLS side.
Yeah. Oh, okay. So you mean the first walk, right? Sorry. How do I get to share the screen? Oops. Doesn't work. So the change of magnetization was about 15%. The change in DMI was about 80%. So from there we know that not all of them is coming from the change in magnetization. Yeah. Stop working. Yeah. So the BLS was performed at NUS. No, it was not micro BLS. Yeah. Yes. This one. Oops, sharing the email. Yeah. Yeah.
I have a back question.
Mhm.
How do you decide which alloy to form? Like
Which phase?
like you showed in the spin Hall angle
Yeah.
versus this plot that they want platinum, titanium.
Right.
There are and you also alloy with oxygen. What makes decide which alloy to be pigment form?
Right. So for our process of thinking, we are kind of limited by the material system that can be deposited on a 200 and 300 millimeter platform. So once we narrow down the elements that can be done, then we go to our collaborators to work out which combination with through DFT. So that is a easier. Yeah. So once we filter down the materials that is possible in our deposition chamber, then we work out with our collaborators to narrow down what kind of choices are available for us.
And how close are the DFT predictions with what you?
So it is kind of sometimes we have a good agreement, sometimes it's not, and mostly because the complicacy is because we are using a cobalt iron boron rather than in the DFT. It's typically cobalt iron. So there is the boron diffusion coming out from the CFB that complicates this picture. And in terms of DMI, it is slightly difficult to predict which first. But in terms of, let's say, other parameters like PMA, right, it is much more accurate. So sometimes it's depending on the questions that we want to look into. Yeah. Thank you. Mhm. Yeah. So this this is actually a theoretical calculation, right? So here, yeah, I will get in. This is a very good question actually. So this theoretical calculation shows that in a very pristine beta tungsten, right, the spin Hall is the highest. And once you increase the oxygen, once you introduce oxygen, it will go down. And if you increase more, it will even go down further. So what we wanted to do is actually introduce only a tiny bit of oxygen, right? Which is what we've done experimentally. But here in this case, we find that our beta tungsten has a lower spin Hall angle, right? So there the difference is basically because in theory, right, it is in the theoretical calculation is a perfect beta phase tungsten. But here we have, like mentioned, after annealing, we have the CAB on top, there is the boron diffusion as well as defects because of it's a very thin tungsten, right? So unlike in the theoretical calculation where you have perfect tungsten, so already the tungsten in our practical case is compromised. So what we have is by introducing oxygen, it is better than the ultra thin tungsten with CFB multilayer, but it is not going to be better than the theoretical calculation of a perfect beta phase tungsten.
We are running out of time, so if you have further questions, fine.
Thank you.
That is short break. And time also for the website. Yeah, I mean, you can. Okay, in that case, we can come back at 11.
Sorry for. Yeah. Oh, this is very tight. Huh? Yeah, this one is very tight. Thank you.
Yeah, you can ask me to take off.
I think we can
Upload it, yeah.
hide floating. Yeah, this. I think this is not a good idea because we just deselect this one.
Yeah, otherwise I cannot move here. This is what I experience sometimes. No, it's not working.
Oh yeah.
This is the next page.
No, this is for the pointer.
Yeah, somehow it's screwed up.
Okay, let me get another pointer.
So we have two mics. This one for Zoom. Then for room, if you want, you can. For
No
room,
need, no need.
yeah, Zoom you can use.
Zoom, okay, I
Yeah.
see. So this
No,
microphone,
just hang it. Okay. This one moving. Yeah, yeah. It will chase you. But not very fast. If you run fast, if you move slowly, it can follow.
This is another one. This one.
But this one only has the
Laser, oh, yeah, I think it's fine. Yeah, because I can use two. Okay. But somehow it's not working. You might have a problem there. So this laser is okay. Is it able to? I don't know.
It is
Wow.
coming.
Oh,
Maybe if you can change the cursor, the pointer side.
but then next page,
it's page.
not working.
Oh, yeah.
Yeah, that's the problem. That's okay. I can use
You-
two.
you-
No problem.
This way.
Manually works, yeah, but
Mhm.
somehow.
No.
Yeah. Maybe we take it out and then put it like this.
Yeah, that's okay.
We have to reset.
Can press this, the second one from the top. Yeah. Yeah, so this is for forward.
Somehow this laser pointer is. I'm not used to this. So this is only this version, sort of not the physical laser pointer.
Yeah,
I see.
I mean, this one, we need some software installation.
Oh, I see. But this one doesn't have a physical laser. No physical laser. I see. High tech.
Good morning, professors and colleagues. So I would like to warm welcome to all of you to today's symposium. So my name is Candy. I will share the next two keynotes. Talks. So we will have two keynote speakers in this session. So the first talk is given by Prof. Hyunsoo is the Prof. US Singapore. So his talk is about Magnon talks. Let's welcome the professor to talk.
Thank you very much. So first of all, thanks to organizing this local event. I think we should collaborate more. Okay, next time we
today I'll briefly talk about this maximum talk before I move. I'll introduce about some background. As you know, STT-M9 is already in the market. Unfortunately, it's already only niche markets like Airbus and Mars Rover because of the space radiation, and then it's very safe. Fortunately, we have global boundaries producing this M9 chip, and Samsung is another boundary service. They produce embedded M9 and they ship to Sony, and Sony integrated Huawei GT2. It's already in the consumer electronics. But how do we expand it from here? That's the question. We have to work together. STT-M9 is the only non-volatile memory capable of high density, high endurance, and fast writing operation. It's the best candidate for embedded non-volatile applications. So that's why many companies are actually working on embedded application. Right now, the most active sector is car or automobile. But we hope we can expand to e-flash in the future, and then IoT wearable, even some small MCU for toy stuff. And eventually, we hope that we can extend the flash application. So what will be after STT? So, we are so excited about this so-called SOT MRAM, and you guys all know, the first work was proposed by this Miron and then Pietro group in 2011. So they proposed the underlying principle to Ashiba. Then immediately Cornell proposed, no, this is actually more. Still, it's not easy to disentangle what is underlying principle. Probably it's depending on the material system and so on. But the bottom line is, once you flow charge currents, we can accumulate spin, no matter what is the mechanism. Then using this accumulated spin, you can switch this mechanism. So this is our writing operation. So introduced by the previous speaker, the quantity of this efficiency of spin accumulation can be defined by so-called spinor angle. Spinor angle is defined by spin conductivity over charge conductivity. Then if you write down the total spin current in this direction versus divide by the injected charge current direction, you can write down this formula. Spinor angle L is your magnetic length, and T is the thickness of the channel. So typically your L is, let's say, 100 nanometer, and T is 10 nanometer. So then you have this L over T is easily 10. So your spinor angle multiplied by 10, that will be the ratio. So that's why spin current can be much bigger than charge current. And initially we were so much excited. Oh, we need to find large spinor angle because this is efficiency of conversion. So then people try to find all kind of materials, including my group, and we found many materials. You can have spinor angle more than 100, no problem. But at the end, it's not useful because typically large spinor angle materials lead to very large resistivity. Okay? Because you need more scattering to generate more partially spin dependent scattering. Okay, that will give you large spinor angle. So eventually, what is most important thing is this spin conductivity, which is defined by spinor angle divided by resistivity, or spinor angle multiplied by charge conductivity. So this is the most important attribute we need to look at. So this is why many interesting 2D materials, they can have very large spinor angle, for example, topological. But eventually it's not very useful because they are very resistant, including many 2D. So once we, this spin torque engineering, spin orbital engineering, once we divide by, to some active layers, the first one is how to generate. So we use a spin, the heavy metal one, because it has large spin orbit coupling. People also pay attention to interfacial effects. today I'm gonna, introduce more on these topological materials. Even two-dimensional electron gas can generate spin current. So once you generate, we need to absorb those using different magnets. Initially, of course, ferromagnet is our first choice because we know how to, make it, pattern it, and use it because it has been applied for many engineering applications. And nowadays, you heard about many anti-ferromagnet claiming, less rigidity, high density, so on. But the problem is the reading is very difficult because it has zero magnetic moment. So it's very difficult for real application. But even though, it's an interesting research area, we should not limit them to only application near future. And capping is also very important. But anyhow, eventually, we have to find this large spin conductivity combination. So today I'm gonna, focus on more these topological materials. This is the so-called 3D topological insulator. One of the typical materials is bismuth selenide. If you look at the band structure, you have this crossing band. So this is so-called Dirac band. If you look at the positive K, it only supports, blue stick, meaning this guy. So when you inject your electrons into one direction, the supported spin is only right angle to the momentum. Now, if you send electron to opposite direction, minus K, that is the red spin, it only supports opposite to the original spin. So people think this is a spin highway, depending on the direction of electron momentum, it only supports one spin. So initially, people expected, oh, it should have a giant spin on angle. So that, it's so much excited many groups' attention, including my group. So eventually, after certain optimization, we found about 8 nanometer is a good thickness to compromise the spinor angle and the resistivity. Not so resistive, also spinor angle reasonably big. Then we put the nickel ion on top. Then we chop down nickel ion into small squares. And if you look at this microscope image from the top view, each yellow square is one nickel ion stripe. So we pattern with a different size because we want to change anisotropy and porosity and so on and see what happens. So once you now inject charge current from left electrode, all the black domain indicate is saturated in this direction, but you can see some white domain, is enlarged, and eventually you can switch everything to white, meaning now it's pointing opposite direction. And now from this geometry, you can inject the charge current from right electrode, and you can see eventually we can, go back to this black state. So we can now go back to the initial state. Depending on the charge current direction, we can switch this nickel ion at room temperature with quite close charge current density. Effective spinor angle, is 1.75, and many people think, oh, how can it be more than 1.1? Because it's a conductivity, not total current. So I think this one really, attract the people's attention. Topological material can be applied at room temperature for 3D ferromagnet switching. So then the one of the criticism was we grow this bismuth selenide using molecular epitaxy. Of course, it's not really industry-friendly technique. So then we try to grow this with the sputtering. So we just bought the sputtering target and then grow bismuth selenide, permalloy, and you can do the same thing. This is a microscope image from the top view. You can see black to white domain, white to black domain with much smaller current density. Spinor angle in this case estimated to be 45. As I told you, you can go any number, whatever you want. But the problem is this one is 100 times more resistive than my MB sample. So that's why you have to roughly divide spinor angle effectively, divide by 100. So then nothing special. This is similar to what Jinping Wang reported in his work. His spinor angle is like 18, and this is their switching current density. So So basically, if you can make a very realistic sample, in general, you will have more scattering. Then what happens? Some portion of this scattering will be spin-dependent scattering. That will give you, so it's not very useful. So then we switch to another topological material called wire semi-metal. This material has more conducting bulk. So you can see from the name itself, previous one is topological insulator. But this is, it's a semi-metal, so it's more conducting now. And it maintained quite reasonable spin polarization. At the surface state, about 80% was measured, and at the bulk, about 40%. So we saw this will be more interesting and low power. So initially, of course, we start with the Scotch tape, so-called Nobel Prize technique. So you do exfoliation, then you find the right thickness, then you can deposit permalloy on top, and we can do the same thing. We apply charge current, black to white domain, white to black domain. You can do this kind of stuff with much smaller, charge current density. And once you calculate the power consumption, we found it's about 20 times smaller than physical satellite case, because the resistivity is about 580 micro cm. And if you think about topological insulator, it's about 1,500 micro cm. So roughly 3 times lower resistivity. Then what happens? Power is, typically square of the resistivity. So we can reduce, 20 times power in this case. So once I summarize this topological material-based spin-orbit talk, number one, we should have room temperature operation. Cryogenic stuff, you can write first paper, but not useful. Number two, we have to move to wafer scale, application. Scotch tape is maybe first demo is okay, but we have to think about wafer scale, also very uniform material. So you can make many devices. We have to improve spin conductivity rather than spin angle, as I mentioned, because of resistivity issue. And number four, previous examples I mostly show in-plane magnetism, which is also not very useful for here, because now industry people are focusing on perpendicular magnetic neutron. So we have to move to PMA switching, and it should be field-free, meaning without any external magnetic field. Then, of course, the fabrication process should be CMOS compatible at the end. Otherwise, nothing will stay. So we try to make it is wire semi-metals, tungsten ditelluride using CVD, because CVD is more CMOS friendly and large area wafer scale. So this is wafer scale fabrication. Then we can do the same thing with the permalloy on top. But still, this is in-plane magnet. But we show, you can nicely switch black to white to black with the reasonable charge current. And this is first demo, actually large scale 2D spin source based exotic switching. But again, from here we have to go to PMA, field-free switching. So then I realized still, once we think about the power consumption, our spin source is either topological insulator or wire semi-metal. Resistivity range is roughly this range, 500 to 1,500 micro cm. We want to use 3D ferromagnet. 3D ferromagnet resistivity is typically less than 100 micro cm. So what happens? When you inject charge current, most of charge current will be shunted through your ferromagnet. It's not going to flow here. So then what happens? We lose basically our generation power. This is a current shunting problem with this large resistivity. So then we thought maybe we should just put the insulator here. Then nothing will go up. Then the problem is how you gonna move your accumulated spin into your magnet. So then the idea is maybe with this insulator, if this is anti-ferromagnetic insulator, it's magnetic but anti-ferromagnetic, and it supports magnons. So then this accumulated spin can change to magnon current and then it will propagate, and probably we can, make selection in this experiment. So that's the idea. So in our structure, we try to use nickel oxide, and then, as some preliminary study by other people using anti-ferromagnetic, transport. Most of people study in plane propagation. Most of them use this alpha base iron oxide. It's a hematite. So then they found this Matis Clowy group. They found even this spin current can propagate, micrometer scale, very long, because it's a single crystal. This is Renshaw group in MIT. Also, they found it can go to hundreds of nanometer using 120 nanometer thick in iron oxide. So then both reported quite low dissipation. But this all in-plane measurements, you can extract some interesting, spin-related parameters, spin diffusion length, this kind of stuff. But actually, in real device, it's not very useful. Because real device is all vertical. You look at MPJ, GMR. All this is a vertical device because then you have advantage of the area, and also very short sort of interaction length. So our case, we use our bismuth-selenide, then we deposit nickel oxide. This is anti-ferromagnetic insulator. Then we put nickel ion. Then we measure, conventional STFMR. So that is this field symbol as a function of nickel oxide thickness. So as soon as we add any thickness of nickel oxide, the spin efficiency drops to 0 almost, which kind of makes sense because you have, some kind of oxide. Why, spin current can propagate along this vertical direction? Because it can just go through, But when we increase the nickel oxide thickness more than 10 nanometer, we start to see the increasement of this spin efficiency, which has a peak at about 25 nanometer, and then efficiency is about 0.3. This is effective spin angle. So how come 25 nanometer thick nickel oxide can support some, spin propagation? And only possibility is magnon. So then, of course, the referee never believe. How can you have this trend with 25 nanometer thickness? I don't believe it. So we had to do inverse measurement. So inverse measurement is basically spin pumping. Because this is the forward measurement, meaning you inject charge current eventually change to magnon and spin torque. Okay? So this is charge to spin converter. Inverse process is we can excite this magnet with a femtosecond laser. Then what happens? We can quench this magnetic moment temporarily. So then it can generate spin current due to the velocity propagation difference of spin up and down. And spin current will go through this nickel oxide using the form of magnon current. Then it can be converted to charge current in this bismuth-selenide layer, and it will generate terahertz emission due to the oscillation of charge. So this is the spin to charge conversion. So that's why we call this the inverse process. So we measure this as a function of nickel oxide. That is shown in the open circle here. So you can see it really follows the trend of STFMI. So indeed, this thickness dependence is correct, and then we can see the existence of this conversion through the magnon current. So to confirm we can really use this magnon current, we need to isolate our magnet, this ferromagnet. So we etch out. So when we inject our charge current, there will be no current flow inside the ferromagnet. So only possibility is current will go through bismuth-selenide because nickel oxide is also anti-ferromagnetic insulator. So the charge current is going through, then what happens? You have accumulation of spin here. Then this guy will propagate nickel oxide. Then eventually you can switch this ferromagnet. So you can see this isolated sphere. The yellow one is this middle ferromagnet. And once we flow the charge current from left electrode, you can switch from black to white. and white to black depending on the charge current direction. So we can really show indeed we can use this magneton current to switch this magnetic isolated element. So why this could be useful? Because right now, if you look at this modern microelectronic device or chip, we have many layers of interconnect, 20 to 30 layers, even though our transistor is only one layer at the bottom, because we have to connect many local, medium and global interconnect. So how to do this? And the industry people need to, etch out so-called via. Then they have to fill, there's a metal, context. It's a very difficult process, modern CMOS process. So if we can, fabricate the device without this kind of interconnect. For example, this ferromagnet, no need to have a physical contact. It's just isolated on top of insulator, but we can switch. I think this can, relax some of the challenges in via and the interconnect. But maybe in the future, probably people can think about some more interesting applications. Okay, so the next question was now, what is the propagation velocity of this magnon inside nickel oxide? So because this terahertz measurement is basically time resolved measurement, you can record its physical time. So as a function of nickel oxide, we can measure when there is no nickel oxide, what is the emitted time, versus when we insert nickel oxide, what is the the emitted time. Then we just look at the time difference. Then divide by nickel oxide thickness. So basically that will give a rough estimation. It's not so accurate because we need to think about the conversion time from, like a spin to magnon and magnon to charge. But we ignore those. We assume maybe that is even much shorter than the propagation time of magnon. So as a first approximation, we extract this time delay as a function of nickel oxide, and we divide by the thickness of nickel oxide. That will give us the velocity. And you can see it initially increase up to about 600 kilometers per second, and then it decreases. And this speed range is extremely fast compared to previous estimation of 40 kilometers per second using Perk inelastic scattering measurement. Of course, it's a very old measurement and it's based on the Perk sample, very thick. So what we are measuring is kind of nanoscale phenomena, which can be very different from the Perk phenomena. And how do we understand? So we had a collaboration with Gyeongjin Lee and KAIST, and once you have damping of the real materials, basically your dispersion is distorted in the small k vector regime, and depending on the this damping parameter, you can see dispersion can be even distorted more. Basically, the derivative of this is connected with the velocity in this frequency and k vector. So basically, you can have very large velocity at this region. So that is our understanding. And in real material, we always have damping. So probably it's useful in the nanoscale devices. So as I mentioned, our next mission is whether we can switch PMA. So we can fabricate this copper and boron now on top of this very thick nickel oxide, and we try to switch this guy using magnon current. And without any external magnetic field, we cannot switch because our injected spin from bismuth telluride or bismuth xenonide is only in plane stuff. So it exactly follows our conventional knowledge of typical spin Hall or large bar system. But once we apply very small in-plane field along the current direction, then we can switch. Opposite magnetic field will give opposite, switching polarity. So the operation of this PMA switching using magnon torque follows exactly the same the conventional spin-oil system. And to prove also, we can switch isolated magnet. We always use our MOC imaging. So this is now PMA isolated copper iron boron on top of nickel oxide, and we just flow charge current. You can see we can switch from white to black or black to white, and in this case is PMA, in plane stuff. But of course, we have to apply very small in plane magnetic field switch. Okay, so as a quick summary, we studied the magnon torque in this structure. We have some enhancement SO efficiency as we use more than 20 nanometer nickel oxide. And the magnon propagation velocity can be very high, more than hundreds of kilometers per second. And finally, we also show it is possible to switch the PMA, but with a small magnetic field. So basically, this magnon torque is strong enough and fast enough to switch the isolated magnetic structure. Okay, for this, I want to thank many of my group members and the previous group members who contributed, and also my collaborators. Thank you very much.
Question is, why do you use the anti-covalent? For example, if you use the INH instead of then any difference. And I have a second question, that what is the propagational length of this magnet propagation length?
Good question. So if we use YIG, some people try to switch YIG directly. So there is ambiguity, because whether my spin current will switch YIG or copper iron boron, and then those magnets can be also coupled. So very complicated. If you have anti-ferromagnet, it's very clear, because there is no magnetic moment in this car. So I'm not switching nickel oxide. My aim is to switch copper iron boron, because this is the material. So this is my aim. Of course, you can study with the YIG water act, but I think the situation will be very complex because it has magnetic moment. You will switch YIG. And what is the magnon propagation length? I think it's a good question. So we try to extract, for example, using this chart. There is a first decay. So once you use the exponential fitting, your magnon decay length is about 1 nanometer. And as I mentioned, this is nothing to do with the magnon. Just because you need a few monolayers to make a long range order. Any magnetic material, you need certain monolayers to make a magnetic order. So you need a few monolayers. So this 1 nanometer, there is no way this is magnetic material. In this range, this nickel oxide is non-magnetic. It's some kind of very dirty sensor. But once you grow more than a few nanometers, now it starts to form magnetic order, proper anti-ferromagnetic band. So once you go more than 10 or 20 here, definitely it's a good anti-ferromagnetic, because we can also measure, for example, exchange coupling, exchange bias, with the other materials. So then we have this second decay. So we use second decay to extract the magnon decay length, and then we estimate about 30 nanometers. And you may think about, oh, this is very short, because previous people found even the magnon can go through micrometer. Because this guy used single crystal, it's a perfect crystal. Of course, it's a different material. But our nickel oxide is better, very dirty, actually. So once you do XRD, we have different phase. 111, 100, 110, it's next. Okay, so it's not really a good crystal. But even though, 30 nanometer, no problem, because we are taking advantage of vertical transfer. The device length scale doesn't need to be very long. But in plane, you have to study at least hundreds of nanometer, because your contact thickness or width is easily 100 nanometer. So separation should be much more than that. Okay? So that's the difficulty in the in-plane. That's why I think it's not useful. Hope, the no audience is working on don't look at stuff. All right.
So in the perpendicular material, said we need what can be the bit of avoid.
Yeah, so it's a good question. If the injected spin has out of plane spin polarization, probably we can switch our magnet without it. That has been demonstrated by some other people, not in the magnet, but with a direct contact in the conventional mechanism, like using tungsten ditelluride. I think there are 3 reports showing we can switch 3D ferromagnet without any that is probably the same direction.
So I mean, people have also reported for the
That's right. That's right. Yeah.
So this scenario of potential.
I think so. Yeah. Yeah. But we've done many different combinations. Sometimes we see this second pump. I show you. Sometimes we don't see a clear second hump. This because I think this is clear evidence of magnetic transfer. And sometimes we see monotonic decay. Sometimes we see those. So it is still not very clear what combination or what physics or materials understanding lead to this behavior. Sometimes we don't see it. So it's it's a really early stage. So we don't know much about it. So we need more people to study more.
Just curious if you have studied the origin of poetry processes in this
We haven't studied. I think it's also a good point.
For your oxygen measurement type elements that introducing nickel oxide enhancing this.
That's right.
Yeah, so
very good.
Giving the power.
Yeah. So very good observation. So right now, if you look at our peak efficiency, it's about half of the peak without. So obviously, we lose our capability to generate, even though we minimize our the shunting effect, but our efficiency is only half because you can think about it. The spinner will go through some kind of conversion process, twice more conversion, because you have to convert from spin to magnon and magnon to another one. So you can see we lose some efficiency. That is the price we have to pay to use magnon. But of course, we hope we can find the system is decay, and the second peak will be almost same intensity. So that's our dream. Or maybe second one will be even higher than the first. So that's the direction we want to study.
Why nickel? Why why not copper or iron larger split pipe?
This is a good question. Typically, this always ends up with what is available in the lab. For example, many people ask this question. Also, I ask many questions when I went to APS or internet. Why you use this material? How do you think about it? Because it's in my drawer. So easy to put it in. Nickel oxide is all these anti-ferromagnet. Near measures exchange bias using nickel oxide. So all these anti-ferromagnet we understand very well, and I did nickel oxide part of my PhD, so I know this material very well, and it has surprisingly the highest yield temperature among many other materials. So we know this guy will work at room temperature. Okay, thank you very much. Yeah.
So the next talk is from Europe. So this talk, something comes to my west on 6 days of
You join the Zoom. Oh, we just, as I mentioned, we just use the time difference in terahertz spectroscopy and divide by the nickel oxide thickness. Can you hear me?
Okay, I think
They can hear.
Yes, sir.
Okay.
Yes, sir.
Thank you. Yeah, welcome.
mute your computer.
studies and progress. So then we solve it.
Technique. So we use the transfer technique. We stack the oxide and the 2D materials together. Simple, straightforward, right? And the interfacial quality currently within our group is still not super high yet, as you can see. So there's a little bit gap between the 2D materials and the oxide. But if you look at the quality of the oxide membranes, it's quite good. So the functionality is there. So we just, although there's some interfacial problem to be further improved, but let's just move forward. Let's see what we can get. So we achieved a transistor. So we combined the strontium titanate and MOS2. We can fabricate a high performance transistor. And it has a very good subthreshold swing, means very good energy efficiency, and also a very good on-off ratio. So it's kind of a state of the art. And on top of that, this technique is also applicable to other combinations. This is the demonstration that we can not only apply the technique to MOS2, which is N-type, we can also apply to the P-type WSE2. I can get the P-type semiconductor, P-type transistors. And then, of course, using the P and NP transistors, we can build inverter, and energy efficiency is very good. Right, so this is about the quality. So this is about the fabrication, what we do. And I just back to the magnetism. So what can we do using the technique? So what kind of spintronics or magnetic study we can do with the technique? So then maybe you can talk about the materials of LSMO, strontium doped lithium manganese oxide. This material is a magnetic material. It has a phenomenon called a colossal magnetoresistance. This means the magnetoresistance is very high. And of course, it's a perovskite. That means we can fabricate them into the oxide freestanding membrane form. And what I'm going to discuss is we use the MOS2 and the LSMO, combine them together, make a heterostructure, and we can achieve the multifunctional device that can responsive to light, electrical field, as well as a magnetic field at the same time. And the device works at room temperature on silicon or silicon dioxide substrate. Okay. First, the property of LSMO freestanding membranes. The LSMO or the colossal magnetoresistance is preserved in the high quality LSMO flakes. So those are the properties of the LSM flakes. So you can see the magnetoresistance, here the magnetoresistance and also the magnetization. Both are well preserved at room temperature, of course, also at a low temperature. So that means the LSMO flakes behave the same as the epitaxial LSMO film. Okay, this is the conclusion. Then we use the same technique. We stack the LSMO and MOS2 together. So these are the optical image and the AFM images. And you can see these are the devices. And also we conducted contact potential difference measurement based on the AFM. Why we do this? Because we want to investigate the band alignment between the LSMO and MOS2. We need to know their work function, the band alignment, so that we can build a proper electronic devices. So that's why this contact potential difference can tell us the information. So what kind of alignment we get here? So the work function of LSMO is typically about 20 plus MeV about MOS2, and this is confirmed by the contact potential difference, of course mapped by the AFM. And then because of this band alignment or the band bending, we can observe the rectifying behavior at the interface between LSMO and the MOS2. The rectifying behavior or the ratio is 10 to order 3 or 1,000 times at if we apply positive negative 2 volts. Of course, this is unique to the heterostructure or the heterojunctions, because if you measure purely LSMO and MOS2, so there's no rectifying behavior. And that makes sense, right? Also standard. Now, because we have this rectifying behavior or this interfacial band bending, we can develop a device called a MESFET. It's not MOSFET, not a metal oxide semiconductor FET. It's a MESFET, metal semiconductor. There's no oxide in between. There's no oxide in between. Now, of course, this MESFET is not something invented by us or by our group. This MESFET is a standard type of device that's being used, invented, I don't know, 30, 40 years ago, and then is still being applied commercially in satellites, etc. Right? So what the the working mechanism is basically the junction here serves as the channel, so we can turn on and off the channel based on the junction. So the MESFET, so we get a good transfer curve and also output curve. So that demonstrates that this LSMO and MOS2 hetero interface can help us build a FET device that's responsive to the electrical field, right? Next, if we can have the device, we can build some circuit. A simple circuit, for example, is an inverter. So this is the inverter, just simply combine the FET as well as the resistor. You can build the inverter with we can also characterize their voltage gain, energy efficiency, and we can amplify the input voltage, as well as we can, of course, study the frequency. Currently, the frequency is still very, the frequency window is still very low. And probably if we really want to get a high frequency device, we need to further develop some other materials. Next, how does the interface respond to the light? So what we do is we have the device, right? We shine the light onto the hetero interface. We, of course, simply characterize their optical behavior. Maybe slightly different with what we conventionally do is we did mapping. The mapping is, look at here, this is the device. In the device, we have SMO and MO2. They are like indicated by the dotted line. And we have the interfacial region, overlap region between LSMO and MOS2 that's there. We use 1 micron laser dot, and we scan the whole region. We scan dot by dot, line by line, pixel by pixel. So eventually we have a mapping or pixel, actually it's a pixel-based image. And in the image, we, of course, while we are shining the light onto the interface, we measure the current or the photo current. And because based on this real space photocurrent mapping, we can see that it's indeed the interface between the LSMO and MOS2